Okay, so I'll just run through tutorial 3 pretty quick. So the first question is find the coordinate vector of v. It's equal to 2, 3 relative to the basis b equal to vector 1, vector 2 in vector space R2. Right, so the first thing that we're going to want to recognize is when we're trying to find, a vector from some linear combination of a basis relative to a basis, is we're just going to look at the vector equal to some scalar of the first one plus the second one plus dot 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 plus so on all the way up to cn bn, right? Because we're trying to find some linear combination for some arbitrary scalar based on the basis. So in this case, what we can do is we can take our vector, set it equal to some scalar of the first one plus some scalar of the second one, and then we can combine those on the right side over here to get multiple equations, right? So we get 2 equal to the first element up here, and the second one, 3 equal to the second one here. Then we get c1 plus c2 equals 2, and c2 equals 3. Now we can form a matrix from these system of equations over here up to here. So we have our augmented matrix, our solution matrix on the right side. Right, then we're going to want to RREF to find the pivots, because those are going to be our solutions. As C1 is going to be the pivot of this one, and C2 is going to be the pivot of this one. Right, so RREF, we just subtract this one, we get the pivot. So C1 is equal to -1, and C2 is equal to 3. Since we wanted to find the coordinate vector, what we wanted to find is basically the coefficients of their scalars, right? So C1, C2, we did that in order, right? Because this is the first one, this is the second one. So our V of B relative to the basis is going to be equal to -1 and then 3. And then we check that, take the first one, put -1 there, take the second one, put 3 there, and we see that it works. Alright, second one's basically the exact same thing, except we're doing with polynomials. So there is a bit of a difference in how we want to approach this. Alright, so we're going to do the same thing again. V equal to some scalar of basis vector 1 plus C2 basis vector 2 plus so on all the way up to the Cn Bn. But here we specifically want to look at the coefficients and their degrees for the terms. Right, so we have some constant 2 and some first degree 3. So what we're going to want to do is take our basis vectors 1 and 2, distribute this throughout the system. Once we do that, we want to group them up into their respective degrees, right? So we have our constant here and our first degree over here, so we're going to factor out an x. Then what we do is we can form an equation from that, right? So C1, C2, these are our constants, so we can set them equal to the constant. Right, so C1 plus C2 equals 2. And we see that C1 minus C2 is with respect to x, which is up to here. So C1 minus C2 is equal to 3. Once again, we're going to set up our augmented matrix, our solution matrix, and RREF to find our solutions for our respective pivots. So once we do that, we get all the way over here. We see that C1 is equal to 5 over 2, and C2 is equal to -1/2. Therefore, our coordinate vector, once again, it's with respect to the coefficients in order. So our first one's going to be 5 over 2. We can check that really quickly. So 5 over 2, 1 plus x, and -1/2, 1 minus x. And we do find that once we simplify this over here, that it's going to be equal to 2 plus 3x. My voice is a bit messed up because I'm sick, but yeah, there's no idea. Sorry about that. This is the same thing again, except it's with the 2 times 2 matrix. Right, so we're just going to do this again. Take this, C1, C2, C3, C4. Some people were confused about this part. Basically what you can do is you can just imagine that, right, this is the first element here, this is the first element here, this is the second one, this is the second one, this is the third one, fourth one, right? So each position within the matrix, right, this is 1, 1, this is 1, 2, this is 2, 1, this is 2, 2, they're all going to be equal to the things over here. We actually see that we can set up our system of equations over here. Right? So C1 plus C2, that's 1, 1, goes to 5, which is 1, 1. C3 is 1, 2, and 2 is 1, 2, so we set those equal together, and so on. But what we notice here, C3 and C4 are absolutely equal to just a singular thing. They're not present throughout the other things. So we can actually just look at equation 1 and equation 4 over here. I like to substitute it as 1 and 2 because we're going to deal with over here. So we have our first equation. We want to isolate for one variable and then sub it into our second one so we can find what that's equal to, and then sub it back in to find what our other piece is equal to. Right, so c1 plus c2 is equal to 5. That goes to c1 equals 5 minus c2. So then we have c1 minus c2 equals 1. This is where we're going to sub it in over here. So we take this piece and we sub it into this. Oh, my marker is quite huge, but we get 5 minus c2 equals 1, which ends up c2 equals 2. Then we can sub c2 back into whatever equation over here. We get c1 plus 2 equals 5, so c1 is equal to 3. Then we just go, therefore c1 equals 3, c2 equals 2, c3 equals 2, and c4 equals 0. So we can set up our coordinate vector of A with respect to the basis, right, which is just 3, 2, 2, 0, right, 3, 2, 2, 0. Or we can set up a matrix over here to solve this. You can do either way, it doesn't really matter, but yeah. Alright, yes, so this one. So here, right, we have t going to p2 to p4. How we end up from p2 to p4 is specifically how we define the transformation t pt, right, with respect to our basis vector b. Right, so if we plug in the greatest degree in our b, we'll notice that we get t squared times t squared, which goes to t4, which is with respect to p4. And so that's basically the greatest polynomial. That's why we have defined it from p2 to p4. But the first thing we're going to do is we're going to take a look at our elements within our b. I like to define it as like b1 is equal to 1, b2 is equal to t, and b3 is equal to t squared, right? So we just have our subscript representing our element. And how we've defined the transformation up here is tpt just goes to pt plus t squared plus times pt. So we can take b1 with respect to pt1, right? So basically pt of whatever is just going to be equal to whatever bn is equal to. So if b1 is equal to 1, pt1 is equal to 1, b2 is equal to t, pt2 is equal to t, and so on, so on, so on. Right, and then we're going to plug in our pt's, our ptn's into our transformations over here. And so what we're going to end up with is, since we have b1 equal to 1, well, pt is then going to be equal to 1, which is going to be t of 1, and we're going to apply that here. So we see that tpt goes to pt plus t squared times pt. So that means t of 1 is just going to go to, well, 1 plus t squared times 1, which is just 1 plus t squared. Similarly, tpt, where pt is equal to t, is just going to go to t plus t squared times t, right, which is t plus t cubed. And finally, b3 is just t squared, so t squared is just t squared plus t squared times t squared plus t4. Right, we actually see that if we check the degrees of our transformations with respect to each other with our inputs, right, so t, whatever's inside of the t, is our input. And we see that the greatest one is t squared, so therefore it's pt, yeah, p2. And we see the output for the greatest one goes to p4, right? So that's a little thing that you can see right there. Now let's find the matrix representing t relative to the bases b and c. So what we can do over here is we can look at matrix. Well, b1 goes to c1, b2 goes to c2, and b3 goes to c3. So what we're going to want to do is we're going to want to take our coordinate vectors for Cn based on our inputs for our t of our Bn, right? And how we would define that is just we do the square brackets over here for t Bn with respect to our coordinate basis vectors over here for C, right? So we take that, that's equal to, since this is C is with respect to B4, we're going to have a constant first degree, second degree, third degree, all the way up to fourth degree. And we store those as our coefficients with respect to each of these variables over here. Right. So now we're going to find it with respect to C over here. So the coordinate vectors for all of them are just represented over here. So we're going to do it with our first one, our second one, our third one. So T1 with respect to C in our coefficient coordinate vector form is just going to be 1, 0, 1, 0, 0, because those are the coefficients with respect to this piece over here, right? Repeat that for TT. We get 0, 1, 0, 1, 0. And finally, t squared goes 0, 0, 1, 0, 1. Right, and how we store our matrix representing t relative to basis according to our transformation p2 to p4, well, this is the end result. So we're going to be looking at the matrix with respect to the columns of our C, right? Because this is P4, this is P4, and we're going to want to store each coefficient matrix vector basically over here as columns in order. So this is the first one, this is the second one, this is the third one. So we're going to store them as columns of one matrix, C1, C2, C3, all the way up to Cn. We see this is the first one, so we put it here, second one, and third one. So that's basically how you approach that one. Yeah, so 5 is quite similar to the last one, right? We're going to look at the elements of our B. Our B1 is just 1, B2 is just t, and B3 is just t squared. However, we've redefined our transformation over here. Right, so we have A0, A1, A2, and once again we have P2, and we see that the final result of our coordinate vectors, well, they're with respect to P2. I've actually shown that over here in pink. Right, this is our A0, A1, A2, constant t, t squared. So we're going to run through all of the elements of our basis vector B with respect to our transformation, and then we're going to store all the results of that with respect to, well, relative to the basis vector B in the coefficients, and then combine them all into one matrix. So let's look at the first one. The first one's 1. So once again, we have B1 is equal to 1. So we're going to plug in that polynomial, because these are all polynomials. You see that PT1 equals 1. Right? PT is not here, but just this is just based on the last one. You can kind of imagine it to be very similar. Right? So we just plug in B1 into our transformation. We get T1. Following the transformation up here, well, we see that we only have a constant term. So we only have A0. And A0 is equal to 1. So we're just going to run through this transformation over here. We see that, well, we have A0 here, and we don't have A1, we don't have A2, so those are all going to go to 0. So we're going to get 3 times 1 plus bracket 5 times 1 minus 0, because we don't have this. T plus 0, 0, 0, blah, 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 so we get 3 plus 5t. Now we're looking at the polynomial, the second one over here, which is t. So this is going to be our A1. The coefficient over here is 1, so we're just going to plug in 1 for all of our A1s. That's 0, that's 0. This is going to be 1, this is going to be 1, and this is 0. So we get negative 2t plus 4t squared. Finally, t squared is our final polynomial. So let's plug it in here. And we get 0, 0, 0, 0, and just, well, 1. So it's just t squared. Now we do our coordinate vectors for our transformation with respect to the basis B. So for equation 1, we get 3 plus 5t, so that means we're going to get 3, 5, 0, because we don't have t squared. T of t with respect to B is just negative 2 plus 4t squared, right? So 0, negative 2, 4. And t squared is just equal to 0, 0, 1, because we only have a t squared. So we're going to combine that in order once again. 1, 2, 3, and that's our matrix. So here we're just going to use the very basic definition for what a null space is with respect to some matrix. So the null space with respect to some matrix M is just taking the matrix M and then setting it equal to 0. Right? So we're just trying to solve that. So we apply that with our matrix A up here. Get null of A goes to the matrix A equal to 0. Then we get the matrix over here. Now we want to row reduce if we can to get our REF. We see that we can actually reduce the first row, so we're going to do that. Then we arrive at our REF. Now from here, what we want to do is we want to recognize all of our free variables. Right, so we have a pivot here, but for the rest, we do not have pivots. We see that this is equal to 0, 0. Well, this is equal, 0 is just equal to 0 for all variables. It doesn't really matter, so this is going to be free. And we have the extra rows that do not exist, right? So that's x3, x4, x5 are free. Now what we're going to do is we're going to let them equal to parameter variables with respect to some field, because we can technically have infinitely many solutions since they are free. So let x3 equal t, x4 equal k, x5 equal p. It does not matter what variables you choose here, just define it as t, k, p, whatever ones you pick, just with respect to whatever field it is. Right here it's not defined. It might be the reals, it might be the complex plane. But yeah, I just picked some field because it's not defined. So now we're going to say, therefore the null of A is equal to, and make sure you do this, the set of x1, x2, x3, x4, x5, right? Because we have 5 columns up here, as I demonstrated over here as well. Which is equal to, then we're going to move everything over for our first row. This is going to become negative, this is positive, this is negative, this is t, this is k, this is p. Right, so negative 6t plus 8k minus p, just move everything over to the b slot. This also has a pivot, so we're going to move it over to the b slot. 2t minus k. And then we just plug in how we've defined them up here because they're free. So x3 just goes to t, x4 goes to k, x5 goes to p. And now we're going to split them up with respect to their variables. So we're going to take our t's, we're going to take our k's, we're going to take our p's. We're going to split them all up into different pieces. And we're going to define the set to be with respect to how we've defined it over here, right? So just bring that down there. That's really massive. Yeah, TKP element of f. Now what we're going to do is we're going to take each piece and we're going to set this equal to the span of vector 1, vector 2, vector 3, of how we split them up. Right, 1, 2, 3, 1, 2, 3. Right, because basically what the span is, once we expand the span, we're just going to end up with a scalar for number 1, scalar for number 2, and scalar for number 3. Which is basically just what we have over here. This is just more concise. And it's what was asked for. Okay, number 7. So, let T be a linear transformation from a vector space V to a vector space W, given a basis V for B for V and 2 distinct bases C and C prime for W. Then the matrix representing T relative to B and C is always the same as the matrix representing T relative to B and C prime. So this is false, and the reason why is we're basically just going to approach this from the idea of uniqueness. Right, so we're going to say basis vectors are not unique. Right, I have an example here for you. If we have a vector space W with vectors, say 1, 0, and 0, 1, then our vectors form a basis for R2 as they are linearly independent and span R2. Now let's move into the next piece. We see that any linear combination of 1, 0, and 0, 1, that's vector 1, vector 2, also form a basis for this vector space. That is, any scalar kc for 1, 0, 0, 1 form a basis for any non-zero set where we have k vector 1 plus or minus c vector 2 and p, and then the next element p vector 1 plus or minus h vector 2. Right, so given they are not unique, we have t for b of c does not necessarily equal t b goes to c prime. That's basically it. Right, and given they are not unique is with respect to the basis. And B, the kernel of a linear transformation T from a vector space V to a vector space W is the set of all V element V such that TV equals 0. And this is true. This is just by definition. That's just how we've defined it. So yeah. C, given an M times N matrix A, the null space null A is a subspace of Rn. We can actually just look back to question 6 to see that this is true. We started with a matrix A, which is 3 times 5, right? So we have 3 rows, 5 columns, right? And we just take the matrix from question 6 over here. We see that we end up with the results of, well, x1, x2, x3, x4, x5. Well, we have 5 pieces. Those are elements of R5, right? So we see that the span as well is also, well, R5, R5, R5. So therefore, the null space, null A, is a subspace of Rn, where Rn is going to be the columns. Right, and since we have a matrix over here by M times N, we have N columns, and we have Rn. So this checks out. Yeah, that's about it for that. Thank you for watching.